All right, you crazy kids, here's your lecture on average atomic mass calculation. Now, before we jump into the calculation, we need to talk about how small atoms really are. So, take a deep breath. Whew, good breath. You just breathed in some neon gas. How much did you breathe in? 0.002% of the stuff you just breathed in is neon gas. So how many atoms does that relate to? Believe it or not, a lot. 5 times 10 to the 17th neon atoms. That's an insanely large number. So even though it composes a very small amount of how much you just breathed in, you breathed in a lot of them. The result, atoms are stupidly small. Now, because they're stupidly small, we had to come up with a new unit to make their masses more relative. So if I use grams for 1 atom of oxygen, 16, I get 2.657 times 10 to the negative 23rd grams. That's just too small. It doesn't make any sense to me. However, if I use a new unit called atomic mass units, or AMUs, all of a sudden the masses of individual atoms are more relative to our brains. They're more like numbers that we are used to using, so they make more sense to us. For example, a proton, neutron, and an electron, if I use AMUs, I can glance at it and see that the proton and neutron are very close in mass. The neutron's ever so slightly more massive, and the electron is very, very small in comparison to the other two. Now, the AMU itself, where did it come from? It was made up, okay? They took 1/12 of the mass of one atom of carbon-12 and assigned that 1 AMU. So carbon-12 has a mass of 12 AMUs. It's just a made-up term, but it makes things more relative for us. Understand that this is not the same as mass number. So the mass number talks about the total number of protons and neutrons. Notice how a proton and neutron are close to 1 AMU. So the mass number compared to the AMU mass is going to be a similar value, but the mass number does not take into effect the electrons or these small digits. So similar values, but still different. Now that we know what an AMU is, we can talk about the average atomic mass calculation. It's the weighted average of all the naturally occurring isotopes of an element. Usually, I make you guys come up with this formula on your own because it's not in your packet. And with some trial and error, we figure it out. But in the interest of time today, I'm going to give it to you. Here it is. So it's the mass times the percentage plus the mass times the percentage plus the mass times the percentage of all the naturally occurring isotopes of any given element. So in this case, if I had 3 isotopes, I would use 3 of these little calculations. And I would add them together. Here is an example of that calculation. An element has 3 naturally occurring isotopes. Great. One of them has a mass of this and a percentage of this. Another has a mass of this, percentage of this, mass of this, percentage of. Oh, where's the third percentage? Oh no. Well, if there's only 3, I could probably add up this percentage. Oh, that's a thick line. I can add up this percentage and get the last percentage of the isotope. A little trick there. What are you going to do? All right, now it says, what is the average atomic mass? What is the element? So what you're going to do is you're going to take the mass and the percentage of each of the naturally occurring isotopes, and you're going to multiply them together, and you're going to add up all those values at the end. We have to be a little careful here. You'll see in my calculation, I used the mass, but then I used a decimal of that percentage. I got rid of the percentage point. By doing that, I'm going to have an answer that's correct or accurate. If I don't do that, my answer is going to be 100 times more than what it should be because you're using percentages instead of a decimal. So just a heads up. So there's my first calculation, and then I'm going to take my second isotope. There's that calculation. And here's my third isotope. There's that calculation. Once again, this value here, 11.01% abundance, I got that by adding my other 2 percentages together and subtracting by 100. Okay, so if I were to multiply those out, I could get these values here, but I have to remember sig figs, or significant figures. So I have 4 sig figs, more than 4 sig figs. My answer is going to have 4 sig figs. Here I have more than 4 and 4. My answer has 4. And here I have more than 4 and 4. My answer has 4. Also with sig figs, I'm going to be now adding these values together. Because I'm adding them, my rules for sig figs change once again. Here I have 2 places to the right, 3 places to the right, 3 places to the right. That means my answer is going to have 2 places to the right, 24.31. And on the periodic table, when I look at that, that comes out to be magnesium. That means all the values in your periodic table have that unit of AMU. So those values you look at, 24.31 or whatever number you're looking at, there's no unit listed, but it is talking about atomic mass units, or AMUs. Let's give you another practice problem. So to confirm the average atomic mass of chlorine with the following data. So here's my data. I would expect you guys to show all of this work shown here in purple highlight to get full credit. All of this will be required. However, in the interest of time, and because I didn't do it, because I wanted to make this quick, here's the two values I'd be adding together, and that happens to be the average atomic mass for chlorine. So that's pretty good. But once again, everything in purple would be required. All right, that's your lecture. Hopefully it makes sense.